Okay, let's dive in. We all face these situations, don't we? Where you've got limited resources, maybe it's space in a suitcase or a budget or just time.
Right. And you need to make the best choices,
Yeah.
the optimal ones. How do you even figure that out? Especially when maybe you want to use the same, I don't know, thing more than once.
Exactly. It sounds like just, life, but it's also the core of so many problems in computing and logistics. Things like packing or even just making chains.
Definitely. And often the way to crack these is using this really powerful technique called dynamic programming, DP for short.
And that's our focus today. We're doing a deep dive into DP, looking specifically at the knapsack problem, but the version where you can take as many of each item as you want, the unbounded one.
And then we'll see how that same thinking, that same logic connects directly to solving problems about making change with coins. Really fascinating stuff.
Yeah. We're drawing heavily from the way it's laid out in section 14.5 of Hello Algo. Found it super clear.
It is a great resource for breaking these concepts down.
So our mission here is to really unpack these problems, not just what the steps are, but why DP works for them. We want you to see the underlying pattern.
Hopefully you walk away with a kind of mental model, right? So when you see similar problems, it clicks. You'll remember how to approach them.
Turning complexity into something manageable. Let's do it. Okay, first up, unbounded knapsack. So picture this. You have a backpack. It can only hold a certain total weight. Let's call that the capacity.
Standard knapsack setup so far.
Right, and then you have a bunch of different types of items available. Maybe gold bars, silver coins, bronze statues, whatever. Each type has a weight, and it has a value.
Got it. Weight and value for each item type.
Now, here's the twist that makes it unbounded. You can take as many gold bars as you want, as many silver coins, as many statues.
Unlimited supply of each type.
Exactly, as long as the total weight in the backpack doesn't go over that capacity. And the goal, maximize the total value you cram in there.
Okay, and that's different from the classic 0-1 knapsack problem people might know.
Totally. In 0-1, you have one of each item, and you decide. Take it or leave it. Just one decision per item. Here, it's how many of this type should I take? Could be 0, could be 1, could be 10.
That unlimited quantity changes everything, and dynamic programming is really well suited for this kind of thing.
Why DP? What makes it a good fit here?
Well, it's about breaking the big problem. Fill the whole backpack optimally into smaller related problems.
Yeah.
We look for overlapping subproblems and optimal substructure. Meaning the best way to fill a backpack of capacity C using the first I items. Well, that solution probably relies on knowing the best way to fill smaller capacities or maybe using fewer items, and those smaller solutions get reused.
Okay, so we build up. How do we keep track of these smaller solutions?
Typically, we imagine a table, maybe a 2D grid, let's call it DP, and DPIC would store the answer to a subproblem.
What's that problem exactly?
It represents the maximum value you can possibly get if you're only allowed to use items from the first I types and your backpack has a capacity of exactly C.
Okay, first I types, capacity C. And the table size would be something like number of item types plus 1 by capacity plus 1.
Yeah, roughly n plus 1 by cap plus 1. If n is the number of item types and cap is the max capacity, those plus 1s handle the 0 cases, like no items or 0 capacity.
So how do we calculate the value for a specific cell, say GPIC? This is the core logic, right? The state transition.
Exactly. To figure out DPIC, you focus on the newest item type you're considering, the ith one. You basically have two choices for how the optimal solution for DPIC might have come about.
Choice 1. The optimal solution for capacity C using the first I items actually doesn't use item I at all.
Right. If the best way to fill capacity C doesn't involve any of item type I, then the value must be the same as the best way to fill capacity C using only the first I1 items.
And we already calculated that. That's stored in DP1C.
Precisely. So that's one possibility for the value of DPIC.
Okay. What's the other possibility?
Possibility 2 is that the optimal solution does include at least one item of type I.
Ah, okay. So we decide to put one of item I in the bag, assuming it fits, of course.
Right. Let's say item I has weight WGTI1 and value 1, using I1 because arrays are often 0 indexed. If we put 1 in, we gain value 1, and we use up WGTI1 capacity.
So the remaining capacity is CWGTI1.
Yes. Now here's the crucial part for Unbounded. We need to fill that remaining capacity, CWGTI1, as best we can. But which items can we use?
Since it's unbounded, we can still use any of the first items, including item I again.
Exactly. So the maximum value we can get for that remaining capacity, CWGTI1, given that we can still use item I, is already stored in DPTTI1.
Whoa, okay, that's the key difference. Not DPI1 CWGTI1 like in 01 knapsack, but DPWGTI1 because item I is still on the table, so to speak.
You got it. That reflects the unbounded nature item I remains available. So the total value for this second possibility, using at least one item I, is the value of the item itself, value 1, plus the best value we can get for the remaining capacity using the first I items, which is DPWGTI1.
Assuming, of course, that C is actually greater than or equal to the weight of item I. Can't use it if it doesn't fit.
Good point. That check C equals WGTI1 is necessary.
So to find the actual value for DPU, we just compare those two possibilities. The value from not using item I, DPI1C, versus the value from using item I, DPWGTI1 plus value 1.
And you take the maximum of the two, because our goal is to maximize value. So the equation becomes DPK ISCO's max, DPI1C, DPWGTI1 plus value 1.
That max is important. Okay, makes sense. Fill the whole table, and the final answer is in the bottom right corner, DPN cap.
That's the one. But that 2D table can eat up a lot of memory if the capacity is huge.
Right. Can we optimize this space, like use just one row or one array?
Yes, definitely. You can notice that to calculate anything in row I, you only ever need values from row I1 or from row I itself, specifically columns to the left.
So we don't need to store all the previous rows.
Exactly. We can use a single 1D array, let's also call it DP, of size cap plus 1. Now, DPC will store the maximum value achievable for capacity C, considering all the item types processed so far.
Okay, 1D array. Now, the tricky bit I always remember with 1D DP optimization is the loop order. For 01 knapsack, you iterate the capacities backwards. Is it the same here?
No. And this is super important for Unbounded. For the 1D space-optimized Unbounded knapsack, you iterate through the capacity C in forward order for each item type, usually from WGTI1 up to cap.
Forward order. Why the difference?
Think about the update rule. DPC equals max, DPC, value without item I, DPC WGTI1 plus value 1. When you calculate DPC, you need the value DPC WGTI1 to potentially already reflect the inclusion of item I.
Okay.
If you went backwards, when you calculate DPC, the value stored in DPT WGTI1 would still be the optimal value using only items before item I. It wouldn't have the chance yet to incorporate item I.
But because we can use item I multiple times, we want DPC WGTI1 to potentially include item I.
Exactly. By going forward, increasing C, when we get to calculate DPC, we can be sure that DPC WGTI1 has already been computed in the current pass for item I, and thus correctly represents the best value for that smaller capacity, including the possibility of using item I.
Got it. So the forward pass allows the influence of the current item I to propagate forward through the DP array within the same item loop. That's subtle but critical.
It really is. Forward pass for 1D unbounded knapsack optimization. Key takeaway.
All right, let's switch gears a bit, but keep that DP thinking cap on. Think about making change. You've got coins, right? Say pennies, nickels, dimes, 1, 5, 10 cents.
Okay. Standard U.S. coins.
And you need to make a specific amount, say 23 cents. You can use as many pennies, nickels, or dimes as you want. Unlimited supply.
Sounds like the unbounded knapsack structure again. Unlimited items.
It does. But the question is different. We don't want maximum value. We want the minimum number of coins to hit exactly 23 cents.
Minimum numbers. And exactly the target amount, not just less than or equal to. And maybe it's impossible. What if the amount was 3 cents and we only had nickels and dimes?
Good point. We need to handle impossibility too. So how does this map to our knapsack thinking?
Well, it maps pretty directly. The coins are like the items. The coin denominations, 1, 5, 10, are like the item weights. The target amount, 23 cents, is like the backpack capacity. And the unlimited supply of each coin is the unbounded part.
Okay, coins are items, value is weight, target is capacity. But the goal is different. Minimum count, exact target.
Right. So the DP state definition and the transition logic will change to reflect this new goal, but the grid structure, the DP idea, still works.
So DPO would now mean the minimum number of coins needed to make amount A using only the first I types of coins.
Perfect. Minimum coins for amount A using first I types, table size again around num coin types plus 1 by target amount plus 1.
And the state transition, how do we calculate DPA? Still two choices regarding coin type I.
Still the same two basic choices.
Choice 1, don't use coin type I at all to make amount A.
If we don't use coin A, the minimum number of coins needed is simply the minimum needed using the first I1 coin types to make amount A. That's DPI1A.
Okay. Choice 2, we do use at least one coin of type I.
If we use one coin of type I, let's say its value is Coincha 1, then we've used one coin, and the remaining amount we need to make is a Coincha 1.
And since we can use coin, again, the minimum number of coins to make that remaining amount using the first I types is DP coins to 1.
Exactly. So the total number of coins used in this scenario is DP a coin to 1 for the remainder, plus the 1 coin we just used. So DP a coin to 1 plus 1.
The plus 1 is key here. We're counting coins, not adding value. Okay, so the transition looks like DP a coin C is the minimum of these two options.
So I see. DP a coin C equals mine, DP a 1A, DP a coin C 1 plus 1. We take the minimum because the goal is minimum coins. And again, assuming a toyancy is big enough to subtract coins to 1.
That min operator instead of max and a plus 1 instead of plus valley 1 makes perfect sense for this problem. What about starting points, base cases, boundary conditions?
Crucial for DP. What's the minimum number of coins to make an amount of 0?
0. You need 0 coins to make 0 cents. So DPI3 should be 0 for all I.
Right. That's our fundamental base case. Now, what if you have no coins available, say I0? Can you make any positive amount A?
No way. If you have no coins, you can't make 1 cent or 10 cents or anything. It's impossible.
So we need a way to represent impossible in our DP table, something that won't mess up the min calculation. If we use a really big number.
Like infinity. But computers don't like infinity.
Right. We need a proxy. Think about the maximum possible number of coins you could ever need to make a Mount Ampton. If you had 1 cent coins, you'd need Ampton coins.
Okay, so you'd never need more than Ampton coins.
Exactly. So if we initialize the impossible states, like dp0a for a 0 with the value amped plus 1, that value is guaranteed to be larger than any possible valid minimum coin count.
Ah, clever. So amped plus 1 acts like infinity. When the min function compares a real count against amped plus 1, it will always choose the real count.
Precisely. And it avoids potential overflow issues if we just try to add 1 to some max and t value.
So after we fill the whole table using the min transition, we look at the final answer, DP target amount. What if that cell still holds the value target amount plus 1?
That means we never found a valid way to make that target amount. The impossible value propagated all the way through.
So in that case, the answer to the problem is MADH1, meaning it's impossible.
Exactly right.
And space optimization. Can we do the 1D array trick here too?
Absolutely. Same logic applies. Use a 1D array, DP of size, target amount plus 1, where DP stores the minimum coins for amount A.
And, let me guess, iterate through amounts A in forward order again.
You got it. Forward order, because the transition DP, Maidakai, DPKai Niases 1 plus 1, relies on DP teen task 1 potentially having been updated using the current coin I. Same reason as the unbounded knapsack.
The pattern holds. That DPI or DP size dependency seems to be the key signal for the forward pass in 1D.
Okay, one more variation on this theme, also from the source material. Same setup again. Coin types, target amount, unlimited supply of each coin.
Let me guess, the goal changes again.
It does. This time we're not minimizing or maximizing anything. We want to know how many different ways, how many distinct combinations of coins can add up to the target amount exactly.
So not how many coins, but how many combinations of coins. Like for 4 cents using pennies, 1 and 2 cent pieces, you can do 1 plus 1 plus 1 plus 1, or 1 plus 1 plus 2, or 2 plus 2. That's 3 ways.
Exactly that. We're counting the number of valid combinations. The objective shifts from optimization to counting.
How does that change our DP approach? The state DPIA must mean something different now.
It does. Now, DPIA represents the number of distinct combinations using the first I coin types that sum up to exactly amount A.
Okay, number of ways to make amount A using first I coins. And the transition, still the 2 choices for coin I.
Still the same 2 scenarios to consider for amount A.
Scenario 1, we don't use coin type A at all.
The number of ways to make amount A without using coin is just the number of ways using the first I1 types, which is DP1A.
Makes sense. Scenario 2, we use at least 1 coin of type I.
If we decide to use a coin I, value coins of 1, we've committed 1 coin. Now we need to make the remaining amount a coins of 1. How many ways can we make that remainder?
Since coin I is still available, unbounded, the number of ways to make the remainder a coin C1 using the first I coin types is DP a coin C1.
Correct.
So how do we combine these? If we're counting total combinations, do we just add them, the ways without coin I plus the ways that involve using coin I?
Exactly. The total number of ways to make amount I using the first I coins is the sum of the ways that don't use coin I and the ways that do use coin I. Or rather, the ways to make the remainder after using 1 coin S.
So the transition is DPI equal DPI1A plus DPI coins 1, A plus sign this time.
That's the key difference reflecting the counting objective. We're adding up possibilities, again, assuming A is big enough.
Okay, max for knapsack, for minimum coins, plus for counting combinations. What about boundary conditions for counting?
Think about amount 0. How many ways are there to make an amount of 0?
Just 1 way, right? Use no coins at all. The
Yeah.
empty set combination.
Exactly. So DA0, 1 for all I, including I0. There's always one way to make 0.
And what if you have no coins, I or O, and you want to make a positive amount A?
How many ways can you do that?
0 ways.
Right.
Impossible.
Right. So DPOA equals 0 for all a 0. These base cases initialize our counting process.
And I bet the space optimization works the same way too.
It does. 1D array, DP of size target amount plus 1, where DPass stores the number of combinations for amount A.
And forward pass for the amounts A.
Forward pass it is, because the transition DPA plus DPA points a 1, in the 1D version, the DPA on the right represents DPI 1A, still needs DPA coins a 1 to reflect combinations calculated using the current coin I. The structural reason is identical.
Wow. Okay. 3 different problems, but that core DP structure and the forward pass for 1D optimization is consistent because of the unbounded nature.
Okay, let's just zoom out for a second. We've walked through Unbounded Knapsack, get max value, coin change year, get min coins, and coin change 2, count the combinations.
3 distinct problems on the surface. But underneath, they feel incredibly similar in how we solve them.
They really are variations on a theme. The common thread is huge. You have a set of items or resources, items, coins. Each has a size, weight denomination. You have a target capacity, max weight, target amount.
Yeah.
Crucially, you can use each item type multiple times, unbounded, and you solve it using dynamic programming on a grid or array.
And that DP approach always seems to boil down to considering the current item I and capacity amount C or A, and you make a decision based on 2 possibilities.
Right. Possibility 1, don't use item I. The solution depends on the state without item I, typically DPR.
Possibility 2, use item I at least once. And this is the key for unbounded. The solution depends on the state for the remaining capacity amount, but still considering item I is available. So it depends on DPI to item size.
Exactly. That DPI part in the use it branch is the fingerprint of these unbounded style problems.
So what makes them different problems then, if the structure is so similar?
It comes down to the specific goal or objective.
Which dictates?
2 main things. First, the mathematical operator you use to combine the results of the 2 possibilities. Don't use versus use. Is it max? Is it min? Is the plus ever? Second, the boundary conditions or base cases you use to initialize the DP table. What does it mean to have 0 capacity? What does it mean to have 0 items? The answers depend on whether you're maximizing value, minimizing count, or summing combinations.
Okay, so objective operator and boundary conditions. And that DPI dependency also dictates the forward pass for the 1D optimization.
You've got it. Understanding this whole pattern, defining the state DPIC, figuring out the 2 choices, writing the transition using the right operator, max, min, or plus, based on the goal, setting the base cases correctly, and knowing about the 1D optimization order, that's the core skill you build.
It's like a template you can apply once you recognize the pattern.
Absolutely.
Yeah.
And you start seeing this pattern or variations of it in lots of different places. Hashtag, tag, outro. So we really dug into 3 classic DP problems today. Unbounded knapsack, minimum coin change, and counting coin combinations. All built on this idea of choices with reusable resources.
And hopefully you've seen not just the solutions, but the why, how the DP structure adapts based on the goal, max value, min count, total ways.
And we nailed down that key feature of unbounded problems, how the take item choice loops back to DPI, and why that leads to the forward traversal in the 1D optimization. Remembering details like that really helps solidify the pattern.
Yeah, getting this pattern down feels super powerful. It's not just about these specific puzzles, right? It's about a way of thinking.
Exactly. It trains you to break down complex decisions with constraints. You see it in resource allocation, scheduling, inventory, finance. Loads of real-world applications share this underlying structure.
So here's something to chew on as we wrap up. We focused on unlimited items today. What if the problem changed slightly? What if you could use each item type multiple times, but only up to a specific limit for each type? Say you have 5 apples, 3 books, 10 gadgets.
Oh, good one. How would you adapt the DP state or the transitions to handle those individual limits? That's actually another well-known knapsack variant.
Something to think about. And maybe look around. Where else in your own work or planning do you see situations that feel like choosing things with sizes to fill a capacity or reach a target? Can you start framing them using this DP mindset of states, choices, and transitions?
It's a great lens to apply. Keep exploring.